nozzle and diffuser coefficients. Up to this point, we have considered only isentropic flow and normal shocks. As we pointed out in Chapter 9, isentropic flow through a nozzle provides a standard to which the performance of an actual nozzle can be compared. Standard isentropic flow a nozzle provides a standard to which the performance of an actual nozzle can be compared. For nozzles, the three important parameters by which actual flow can be compared to the ideal nozzle flow are nozzle efficiency, velocity coefficient, and discharge. Nozzle efficiency, velocity coefficient, and discharge coefficient. These are defined as nozzle efficiency eta n, is defined as actual kinetic energy at the nozzle exit kinetic energy at nozzle exit with isentropic flow same exit pressure PE or KE actual, KE isentropic, and PE S PE actual. The efficiency can be defined in terms of properties. On the HS diagram, state I0 as shown in this picture. State I0 as shown here represents the stagnation state of fluid entering the nozzle. H0i or state 0i stagnation state at inlet. State E represents the actual state at the nozzle exit. Actual state at the nozzle exit, and the state S represents the state that would have been achieved at the nozzle exit. State S the state that would be have achieved at the nozzle exit if the flow had been reversible and adiabatic. Adiabatic and isentropic. To the same exit pressure. In the term of this state, the nozzle efficiency eta n HO H0i HE H0i HS. Nozzle's efficiency varies from large nozzles usually have higher efficiency than small nozzles, and nozzles with a straight axis have higher efficiency than nozzles with curved axis. Nozzles with a straight have higher efficiency. The irreversibilities which cause the departure from isentropic flow are primarily due to frictional effects and are confined largely to the boundary layer. The rate of change of cross-section area along the nozzle exit is an important parameter in the design of an efficient nozzle, particularly the divergent section. Detailed consideration of this matter is beyond the scope of this text, and the reader is referred to a standard reference on the subject. The velocity coefficient CV actual velocity at nozzle exit velocity and nozzle exit. With isentropic flow. To same exit pressure. It follows that the velocity coefficient is equal to the square root of the nozzle efficiency. The coefficient of discharge. CD, actual mass rate of flow, mass rate of flow with isentropic flow. With isentropic flow, in determining mass rate of flow with isentropic conditions, the actual back pressure is used if the nozzle is not choked. If the nozzle is choked, the isentropic mass rate of flow is based on isentropic flow and sonic velocity at the minimum section. That is sonic velocity at the exit of a convergent nozzle and at the root of convergent divergent nozzle. The performance of a diffuser is usually given in terms of diffuser efficiency. The performance of diffuser is usually given in terms of diffuser efficiency. Which is best defined with the aid of HS diagram. On the HS diagram of this picture, in this picture, state 1 and 0, 1 are the actual and stagnation states of the fluid entering the diffuser. State 1 and 0, 1, actual and stagnation states of the fluid. Fluid entering the diffuser. Stage 2 and 2, 0, 2, 2 and 0, 2. Are the actual and stagnation state. Of the fluid leaving the diffuser. State 3 is not attended in the diffuser, but is the state that has the same entropy as the initial state and the pressure of isentropic stagnation state leaving the diffuser. This state, the efficiency of the diffuser can write as this expression: eta diffuser delta Hs on H3 minus H1 H01 H1 H3 H02 H1 as shown in this picture. This is the point 3. Eta D also can be write for ideal gas. T02 CP0 T1 C1 S square V1 S square S square and T3 P1 Therefore, we can write the final relations as eta for diffuser, the pressure of P1 P0 on P1 P02 they also can be write as this relation.